Xilinx is proud to announce the UltraScale 30 gig GTY transceiver is compliant to the most challenging and desired of data center Ethernet standards, the 100G based CR4 and 100G based KR4 electrical standards. When the range offered by potentially expensive 100G optical interconnects is overkill, direct attach cables become the data center interconnect of choice for pushing 100 gig bandwidth to the top of the rack, with 100 gig backplanes supporting those server-to-server interconnects. Now, to do this without requiring retimers, utilizing the transceivers on the FPGA itself, that is game-changing. You can make your server rack solution cheaper and more power efficient. We have an example of each of these systems. On my right, I have a pair of VCU 110s connected via KR4 compliant FCI backplane. On my left, a pair of VCU 108s connected over 5 meters of cable. Let's take a quick look at the design running on both. Both boards feature the Virtex UltraScale FPGA running 100 gig Ethernet example designs. This design has traffic generators and checkers connected to the integrated 100 gig Ethernet MAC blocks with RSFEC implemented in the fabric between the CMAC and the 4 GTY transceivers. The GTY are each running at the standard 25.78 gigabit per second for the 100 gigabit per second aggregate rate. This means real data is running over these links, and we can see the result on the GUI on the screen here. So what makes this so impressive? Let's take a look at the KR4 specification. There are 4 tests that need to pass with losses from 16 to 35 dB and identical COM values across the board. That means anything from 0 to 10.3 millivolts of injected crosstalk, depending on the test. That is not a friendly environment for any serial interconnect, let alone one running at 25 gigabit per second. CR4 is very much the same story, with slightly different test points to account for the different form factor. If we take a closer look at each, we can see that the VCU 110s are connected over a stressful IEEE 802.3bj channel. This channel, including the 110s themselves, comes out to about 37 dB. To truly see whether this channel or the channel you're designing is compliant to the 100G based KR4 spec, we have assembled a simulation environment to verify both the compliance of the channel and the robustness of our transceivers over that channel. IEEE 802.3 Clause 92 and 93 have a number of tests the channel needs to pass to ensure compliance, such as insertion loss deviation, return loss, and others. By inserting the S-param for the channel into the simulation schematic here, those tests are automated. This KR4 channel in this simulation is compliant, so we can go the extra step of showing the expected performance using the IBIS AMI models for the GTY transceiver. The IBIS AMI model replicates the auto-adaptation of the GTY's equalization, and you can see that the resulting post-EQ BER contours give plenty of margin. Not only that, they match the I-scan taken over this same channel in hardware. The VCU 108s have QSFP28 cages, which we are using to connect the 5-meter direct-attach copper cables. Again, right about 37 dB total. The reason that Xilinx transceivers are able to perform over these channels is twofold: superior high-speed clocking performance and fully auto-adaptive equalization. Clocking is fundamental to producing low transmit jitter and enabling the receiver with the best starting margin. The auto-adapting equalization is what allows us to capitalize on that margin and perform equally well over a variety of channels that you might have in your system, and to do so without using your time to tune each link of those interconnects. Virtex UltraScale FPGAs are in production now, so anyone looking to cost optimize their server racks with cheaper copper cabling can start designing them in right now. Go to xilinx.com to learn more, and thanks for watching.